Hello and welcome to a new session of classical motion of a single particle. So, previously we discussed about the different features of a conservative force field. We said a conservative force field is a force field which has a zero curl, and also we said that conservative force field, the total mechanical energy is conserved, and that was actually the outcome of the fact that the force field could be written as a gradient of a scalar function which we call potential. Okay. So, if you now see, we also raised this question that if f is equal to minus gradient of psi or plus gradient of psi, actually does not matter. In both cases, since curl of a gradient is 0, then curl of f is 0. Now, the question is the converse true? I promised you to show that much more rigorously, and so in this lecture I will actually discuss this point, that if we know that curl of f is 0, then can we actually say that f is always equal to plus minus some gradient of a scalar function? I have just written this minus sign for the convention, but it can be actually plus minus of a gradient. Okay. So, how would we proceed to show these things? So, let us first start the demonstration by using the property of zero curl of f. Okay. So, we are just saying that since curl of f is equal to 0, then of course, we know I j k del del x del del y del del z f x, f y and f z. This is nothing but I cap del f z del y minus del f y del z plus j del del z f x minus del f z del x plus k cap del f y del x minus del f x del y. Okay. And according to our given condition, this is a null vector. So, every component of this vector will be 0 separately. So, that is actually, that means that del f z del y will be exactly equal to del f y del z, del f x del z will be exactly equal to del f z del x, and del f y del x will be exactly equal to del f x del y. Okay. We will now use this fact to show that if curl of f is 0, then f is gradient of a scalar function. We will first go to evaluate the work done. So, if you again, the point is that if we just say that this is the work done W to bring a particle from some point, initial point to a final point, then f dot dr from that initial point to that final point will be the total work done. And unfortunately, in general, this work done is not a state function. So, for example, d of W is not a d of a state function f, and that is in general the problem. How can we understand this thing? If your f is a state function, then d of f can be written as del f. So, if let us say f is a state function and it is just a function of x, y, z, these three spatial coordinates, then df is equal to del f del x, given y and z are constant, dx plus del f del y dy plus del f del z dz. Okay. Of course, here x and z are constant, here y and x are constant. Okay. So, you see that whenever you write this type of thing, then you can actually say that this is an exact differential, and whenever you just integrate an exact differential, for example, d of f, then you know this is exactly equal to f, and if you integrate, for example, from some point x1, y1, z1 and 2x2, y2, z2, then this will be just the value, the difference of the value of f in x2, y2, z2 minus and I mean the difference between this value f of x2, y2, z2 and f of x1, y1, z1. If you have an inexact differential, or if you have a non-state function, for example, this is the case for this work done W, then when you integrate, so for example, if I say that f dx, okay, I actually have to know the exactly the dependence of f on x, and if I say that is from some xi to xf, then I directly cannot write this as some value, let us say f at some xf xi or some value g at xf by xi. Okay, I have to actually know the exact dependence of f on x, okay, and that is why we say that it depends on the path chosen. Okay, so how it is not only that it is not depending only on xi and xf, but it is also depending how you are going from xi to xf. Okay. So, this type of thing once again is very easy to understand. Again, by this example I have said, once again I am repeating, it is always good to revise those concepts. So, let us say you have a variable y, okay, which is somehow depending on x. So, y is a function of x. Now, if I say y dx integration from 1 to 2, then actually you you have to know that whether that y is exactly equal to x, or y is equal to some beta x square, or y is equal to e to the power minus x, otherwise you cannot integrate to evaluate. But if I say integration over 1 to 2 d of x y, then if I then say that the value of this xy, so xy I can call as z, and the value of z integrated from 1 to z is equal to 2, then you know this is nothing but d of z from 1 to 2, then it will be simply z 2 to 1, so it will be 2 minus 1, 1. So, that is exactly the difference between when you are calculating state functions or point functions and the path functions. Okay. Here you see we have to somehow show that this dw is actually is actually d of some state function, let us say phi xyz. Okay. In general, what we know that dw is this thing, and if you are already familiar with thermodynamics, maybe you also know that if we are talking about an infinitesimal quantity which is not a d of a point function, we in general use this. It is called d-cut w. Okay. So, it is called an inexact differential. Okay. Now, what we will show that if the curl is 0, then somehow we have a special case where this d-cut w is actually d of some function phi xyz, maybe that we will show. Okay. So, once again we start from the definition of w. So, w's definition, so d-cat w is so d-cat w is actually this, and w is integration over this. So, let us consider, or let us assume that we are trying to bring a particle from some x1, y1, z1 point to x, y, z point. Now, here this x1, y1 and z1, this is a known point, known initial point, and this is an arbitrary final point. So, this is just an arbitrary variable, and this is we know, for example 0 0 0 or 1 1 1, and this is an arbitrary x y z. Okay. So, we can actually then write, if we know that f is nothing but f x plus f y j cap plus f z k cap, then we actually know that this will be simply integration x1 y1 z1 to x y z f1 x y z dx plus fx fy x y z dy plus fz x y z dz. Okay. And of course, you know that this is in general not a point function, this is a function where this to evaluate this integral you have to actually know the functional dependence of fx, fy and fz on x, y, z. So, this is something we have to now tackle. Okay. We will now try to perform this work, the total work done in a specific path. Once again we can say that this one, the value of w from bringing a particle from this point to this point depends on the path chosen. So, for example, if this is the initial point, this is the final point, if you are taking to this by this path or this path or this path, actually the w should be different. Okay. If we do not know anything about the nature of the force, but somehow if the force is conservative, then we will actually show that this actually is same in for all the path chosen. So, how to do that once again? So, we choose a special path. The special path is actually like this. I am writing and then I am explaining. So, you see the special path is a little bit special in this way that first we start with this all three coordinates, then we selectively vary only the x coordinate, keeping a y coordinate and z coordinate constant. So, basically what we are doing? We are doing a partial differentiation with respect to the spatial coordinate x, and then we actually change y only, keeping x as x and z1 as z1. So, y is now changed from y1 to y, and finally, we do not change x and y, but we only change z1 from z1 to some arbitrary final value z. So, in this way this can come from this point to this, the particle can come from this point to this point. Okay. It can be done in any other way, we have just taken this special path. So, if we do that, then what will be the total work done? So, the total work done will be actually integration over x1 to x f1. Of course, you see that f1 x comma y1 comma z1 dx plus y1 y f2, sorry, it should be fx not f1. Let me check whether I have written this. Okay, yes, fx fy x y z1 dy plus integration z1 to z, yeah, fz x y z dz. Okay. Now, what exactly the reason for writing this? So, actually the proper writing is, I am just writing and then I will erase this part. So, the proper writing is actually, so f dot dr integration with this special path c star is actually equal to integration x1 y1 comma z1 to x y1 z1 plus x y1 z1 x y z1 plus integration x y comma z1 then x y z the sum on these three uh, part integrals, or I mean how to say, the sum of these three sub integrals which are working on this. Now, for this first integration, you see it's only x is changing. So, dy and dz will be 0, and that is why from this first one I have only this contribution. From the second one I have dy is non-zero, but dx and dz they are 0, that is why I have this. And for the third, from the third one I have dz is non-zero, but dx and dy they are 0, and that is why the whole thing actually. So, actually this is I mean all these three integrals are working on all the three, I mean all the f dot dr, but you see that the special, according to the special root, we have actually for each step of the root only one variable which is changing. So, you can actually do this at your at hand. You can do this yourself to check that this is exactly equal to this one. I am now coming to this point once again. So, I have this is the total work done. Okay. Okay. Now, if I write this thing del w del z, you see this is exactly equal to just this part f z x y z. Why this is just this part? That is because if you see that del w del z means that I am just changing w only by changing z, and here the variation in w, they are actually segmentized in three parts, and this is the part where only z is changed. So, when I do exactly del w del z keeping x and y conserved constant, then actually it is nothing but this part which is coming. What is my del w del y keeping x and z constant? Yeah. So, you see this is the part where you can actually think that okay, maybe this is only this part. Now, there is a trick. You see that whenever I have, so of course this part will come f y, that will come. So, here the f y is a function of x, y, z1, that will of course come, but it will also act on this part, because you see here the this x and this y, this is actually already a variable. So, you can actually write this is nothing but z1 to z del f3 del fz del y, and that will be a function of x, y, z times dz. Okay. That part will be possible, because you see the thing is here the trick is that since okay, why okay, once again, many a times we have this confusion, so I want to clarify. When I take this del del z, you see z1 we know, so only z is variable in this part. So, that is why this is coming only from this one. Here for this one, y is known in this part, but y becomes an arbitrary variable right from this one. So, here you have a y and here you have an y. So, whenever, so let us say now this one is integrated over z. Now, this is still a function of x and y, okay, and that is why del del y of that will not be 0. So, that is why this del del y will act, and this is actually will commute with the integration which is only on z, and that is why you have finally this. Now, since you see here we will smartly use the curl 0 condition. Since we have a curl 0, then we have these equations. And what is del f z del y? So, del f z del y is nothing but del f y del z. So, I can write this as del f y del z with the same variables x, y, z, okay. And this is then this is nothing but, this whole thing is nothing but a very simple thing. So, del omega del w del y is then xz constant, okay, is then simply f y x y z1 plus integration z1 to z del f y del z x y z dz. Now, what is this simply? This is, you see, that nothing but, so the first one is f y x y z1, the second one is simply f y. So, it is only a differentiation on z, partial differentiation, and it is integration on z. So, they can nullify each other, okay, the effect of each other is nullified, and that is why you will simply have f y at x y z1 z, okay, minus f y x y z1. Now, this one and this one will go away and you will simply have this, okay. I can do the similar thing with the last one. So, I will now calculate del w del x, and this is exactly equal to f1 x y1 z1, but you see x dependence is here, okay, because I have changed x from x1 to x right from the first step. So, if this is the case, then I actually have two more terms, which is y1 to y del f y del x x y z1 dy plus z1 z del f z del y. I have to check actually. The first one is, so when I take del x, so this will simply give you fx, this one will give you del fy del x, and I mean times dy, and then it will give you del fz del x dz. Yeah. Yeah. Del x x y z times dz. Okay. Now, you see this is simply fx and you have x y z1 plus, now what you have, again using zero curl condition, you will simply have, this is nothing but y1 to y, this will be del fx del y x y z1 dy plus z1 to z, this will be zero curl by zero curl condition. So, again I am writing like this so that you can understand, by zero curl, this will be del f x del z, change, yes, del z x y z, okay. I am just writing by zero curl, by zero curl. So, I write del f x del z dz. Now, what is happening? It is a beautiful result, as you can see, f x x y z1 plus, what is this? It is simply I think f x x y z1 minus, so this I mean will be simply f x in this, I mean the difference of f x in this two limits, okay, within these two limits. So, minus f x x y1 z1, this is from this one, okay, this two came, and from the last one we will have then finally plus f x x y z minus f x x y z1. You see f x x y z1 goes away, So, this is x y1 z1, I just y1, yeah. So, to be very honest, this will be a y1, and so this is actually going away with this one, and this one is going away with this one actually, okay. I mean, does not matter finally. So, yeah, I can just make all this, yeah. So, once again, this one goes away with this one, and this one, this is x y1 z1. So, this goes away with this one, okay. I write like this, yeah, and this one x y z1, this goes away with this, okay, yeah. So, finally, I am left with this, okay. So, you see, now I have a condition where I have f x dx plus f y dy plus f z dz is nothing but del w. W is now just a, I mean, you can see that w is just a function of one point. This is x y z, you see, and this is nothing but this plus del w del y dy plus del w dz del z dz. If you just see all these things. So, right from this and this, you just accumulate and you just say this, and you just multiply dx, you just multiply dz with this part, you just multiply dy with this part, and you just multiply dz with this part, and finally you will get this one. I can call w as minus phi, which is a state function, okay, and you can simply say this is nothing but minus of del phi del x dx minus del phi del y dy minus del phi del z dz, and this is nothing but minus grad phi, okay, dot dr, okay. So, you see, this is nothing but f dot dr, and which is nothing but equal to minus of grad phi dot dr. So, simply it means that your f is equal to minus grad phi, okay. So, from this I can conclude this. So, here I actually complete the proof by showing that if I take this special path, then my work done, I mean work done due to a curlless force is actually a gradient of a scalar function. Now, you see, not the work done, I mean the work done is independent of the path chosen, the force is actually a gradient of a scalar function, okay. So, once again, if I calculate the work done due to a curlless force F, then the work done is a state function, and the force field can also be written as a gradient of a scalar function, okay, with plus or minus sign according to your convention, okay. So, you see, this completes the proof by saying that if a force field can be written as a gradient of a scalar, its curl is 0. If a force field is curlless or have 0 curl, then it can be written always as the gradient of a potential or the scalar function, which is known as the potential, okay. And this proof can also be done alternatively using a theorem called Stokes theorem, that is also very interesting, an integral theorem, okay. So, if I have some time, I will also talk about that. Now, this actually does not complete the proof 100%. So, you can say, okay, I have shown this specific form for one case. Now, the point is that for a given force field, I have just chosen any path to show that the work done is independent of path. So, it is actually then possible, I mean it is actually then sufficient to reason that this is, I mean if it is independent of path for any special path, if the value of work done is just giving you that is independent of path and it is only the function of the final state and the initial state, then it will be true for any other path. So, in general you can show that the work done under a curless force is independent of path chosen. Okay. So, as I discussed in the previous lecture that for conservative force fields and especially like for central force field, you will actually see that this is the cause why the work done is independent of the path chosen. Thank you.